Okay, well, good morning, everybody. So today's the last day of class. Finals next Wednesday, 9:10 in the morning, right? So I think you all know when your final exam is. I've also put on the board my office hours for finals week. So since both of my final exams are on Wednesday, I'm just front-loading the week with office hours. So I'll be here Monday and Tuesday. And hopefully if you have any questions, you'll be able to come find me. Anyway, so today there's really no new material. I mean, I will summarize what we covered last time like I tend to do. But beyond that, the rest of the day is really just a day for review, question and answers, teacher evaluations, and I'll just do that at the very end. Also, let me just remind you that I do have some old homework, so if you haven't picked up your work, let's see, Dideon, Sargassian, and Hull, if you guys are here, please don't forget to pick up your work. So, just the brief summary from last time. So the last topic that we covered was combustion, right? When we first talked about combustion, which was last week, we were just looking at the combustion of a hydrocarbon gas like methane or propane, something like that. And we just looked at the situation where we had the stoichiometric mixture of air and fuel. In other words, the chemically balanced amount of air to burn with the fuel to produce the carbon dioxide and water vapor as combustion products. But we also talked about, and this would be last time now, how in the real world, if you just burn the fuel and air as a stoichiometric mixture, you're not going to get the combustion to go to completion. You're going to end up with, say, carbon monoxide instead of carbon dioxide and other incomplete combustion products. So we always add excess air. So after we looked at the stoichiometric equation for combustion, we then looked at the actual combustion equation that did consider the excess air that we would have to utilize. Now, the only real difference between our combustion equation, that is our stoichiometric combustion equation, and the actual combustion equation is simply going to be a term that goes right in here, which is our theoretical air fraction, right? This would then be multiplied by the stoichiometric coefficient, and then we have our air. So this is what the left-hand side of the equation would now look like. Now, I use TAF for theoretical air fraction. The author simply calls this the percentage of theoretical air. It doesn't even use the TAF notation or fraction notation, but we need to use fractional data here. We can't use percentages, right? Let's also keep in mind that what we call the theoretical air fraction is really just 1 plus the excess air fraction. So in some problems, you'll be given the percentage or fraction of excess air. Maybe you're told that there's 20% excess air, in which case this is just going to be 1.2, right? In other problems, we're going to be given the theoretical air fraction or percentage. Maybe you're told that you have 150% theoretical air, which means you have 50% or 0.5 as excess air. Now we need to know that there's a difference between theoretical and excess air. They're certainly related, but not quite the same. Nonetheless, after we go through our combustion process, we're going to still have A CO2s, we're still going to have B over 2 H2Os, but with excess air, that means excess oxygen, so we're going to have the excess oxygen. So that's just going to be the excess air fraction, not the theoretical air fraction, but just the excess air fraction, and then times the stoichiometric coefficient O2, right? So this is going to be what was not used for combustion into CO2 and H2O, right? The 1 corresponds to the amount of stoichiometric air that we would need, right? That gives us A CO2s and B over 2 H2Os. The excess air is just there to make sure that combustion moves to completion. It's all going to come out as a combustion product, oxygen. And then, of course, this isn't quite finished. We also have our nitrogen. So however much nitrogen we start with is certainly going to be the same as what we end with as a product. So this then would be the combustion equation So as long as we know the amount of excess air or the amount of theoretical air, we should pretty easily be able to go through this equation. Now, once we've gone through that equation, then we can do everything else, right? And when I say everything else, we can determine the air-to-fuel ratio. That's always going to be important to us. We can also determine the partial pressure of the water vapor in the combustion products. That's going to be important to us. And of course, it's not important to us because we want to know what the partial pressure is. It's important because that allows us to find the dew point, right? The saturation temperature at that partial pressure. That's the dew point. And that becomes an important number, especially if we're designing furnaces and smokestacks and all that. We definitely need to make sure that we don't drop below the dew point temperature in our combustion products, or else, well, again, we talked about this before, right? Water vapor is now going to condense into liquid water. It's going to react with the oxides of sulfur and nitrogen as pollutants in the combustion products and then form acids, right? Sulfuric acid, nitric acid, which get into the environment and cause all sorts of damage. The damage is certainly already occurring. Fortunately for all of us, we kind of figured this out about 40 or 50 years ago, that combustion products were creating acid rain. Nobody knew back then why all the forests in the northeast of the United States and eastern Canada were just dying. No reason, but of course we figured it out, right? So that changed things in the combustion industry, let's say in the power industry, and now everybody has to clean up their pollutants. Pretty much no sulfur and no nitrogen is now released into the environment in big power plants, at least modern new power plants. Maybe I shouldn't say no, but a much, much, much less amount than, let's say, we would have seen 30, 40, 50 years ago. So nonetheless, hopefully we're not going to have acid rain problems in the future. I suppose there's always going to be some. I mean, you have combustion, right? You're always going to have oxides of nitrogen as combustion products, not based on complete combustion, but based on the real world combustion. We're going to have nitrogen that's going to form NOx, and that's going to be a pollutant. Can't do anything about that entirely, but we can certainly minimize that. One other thing I might note, as long as we're talking about combustion, you can certainly note that the two combustion products of interest are water and carbon dioxide. Frankly, we don't care how much water is released into the atmosphere following a combustion process. Water's not our problem. The problem is carbon dioxide, right? Carbon dioxide, we now know, is a greenhouse gas. Well, at least all of us except some of our people who work for our current president and who work for the EPA. These are the people who should embrace science, but they're not. And I mean, I can't even get into that now. I'm on tape. But nonetheless, most intelligent people realize that carbon dioxide is indeed causing our planet to warm. There's plenty of evidence of that now. And we really need to minimize our CO2 output. One way we can do that is by picking the appropriate fuel. If you look at a typical fuel, let's just say gasoline, the ratio of hydrogen to carbon atoms is about 2.5 to 1. 18 to 8 is the actual ratio. So about 2.5 to 1. On the other hand, if you look at natural gas, which is mostly methane, methane being CH4, there's 4 times as much hydrogen as there is carbon. So if we could wean ourselves from, distilled fossil fuels, gasoline, diesel fuel, and all that, and start using more natural gas, then we could significantly cut down the amount of CO2. I mean, from the combustion of 1 molecule of gasoline versus, let's say, 1 molecule of methane, we're going to have, much, much less carbon if we burn natural gas, and that's a good thing. So hopefully we'll start moving in that direction. People like me have been hoping we would be doing this, or would have been doing this, for a dozen or dozens of years, but it's just never happened. It's beginning to happen. Coal plants are being shut down all over the country, much to our president's chagrin, because he likes the coal industry. But it's the worst. It's the most polluting. It's the one that we really need to shut down. And natural gas is really cheap now with hydraulic fracturing. We can get as much natural gas as we want, dirt cheap. And that's really where industry is headed right now. Burning natural gas and using it in place of coal or fuel oil, which is really going to be helpful to all of us. So any questions then, just in general on combustion? Good. I have to put my pen down. So that really finishes the material for this class. And now what I'd like to do is just everything else. So I'm never sure if I should start by talking about the final or going through a review or asking for questions, so I'm just going to start with a review. My intention is not to fill up the board with equations. In fact, I'm hoping I don't have to write anything on the board. I'm just going to discuss in general the kind of things we've talked about, the kind of problems we've seen, hopefully so that you remember these things prior to taking your final next week. After that, then I'll just open it up for questions. In fact, as I'm going through this review, if anybody has questions about anything, pertinent homework problems in that section or whatever, then please just raise your hand and we can talk about it. Or if you're more comfortable, just make a note of the questions you have and we can talk about that later. And we will talk about the final exam later as well. So, review. The first thing I did was my own review, right? I spent the first couple of days just going through a review of the important things from your first course in thermodynamics. Much of this was just making sure you remember the nature of properties and you know all the notation and terminology, that you understand closed systems versus open systems, that we understand how to apply the first law of thermodynamics, that we also understand the nature of the second law of thermodynamics and concepts associated with that, like isentropic efficiencies when you have steady flow devices like pumps, turbines, and compressors. We talked about all these basics. We were able to calculate things based on the first law, rates of heat transfer, rates of work production, in other words, power. There were all sorts of things we were able to calculate. We looked at thermodynamic efficiencies as well as isentropic efficiencies for different, at least for the general heat engine and refrigeration cycles. This was all part of the review. And then we started talking about the new stuff. I think the first thing that I talked about was how does one use air tables, table A17, when we're dealing with ideal gas problems, which is much of what we covered this quarter, right? Ideal gas problems can be solved either assuming constant or assuming variable specific heat. Variable specific heat is more accurate, but that was not something that I covered in my first course in thermodynamics. So that's why we talked about variable specific heat, using table A17, using things like relative specific volumes and relative pressures to analyze isentropic compression or expansion processes. So that was really one of the first things we did. And then the new material. Some of it wasn't even new. I mean, at first we talked about gas turbines, right? This was the first of our gas power cycles. Gas turbine, I'm sorry, that's not right. We first talked about reciprocating engines. So I take that back. Within gas power cycles, we talked about internal combustion engines, basically, reciprocating engines. I mean, we're really only looking at one piston cylinder at a time. But still, this is the basis for our analysis of internal combustion engines. We looked at two different models. One model which does a decent job of modeling our spark ignition engine, in other words, gasoline engine, one that requires spark plugs. That was called the Otto cycle. The Otto cycle is an air standard cycle, but we could solve it either with variable or constant specific heats, right? We also looked at another model, which is the diesel model, and this is used to model a compression ignition engine, a diesel engine, if you will. But both engines are similar. I mean, in both cases, we start with a fuel-air mixture. Now remember, we're only dealing with air standard cycles, so it's not really a fuel-air mixture for our analysis. For us, it's just air. But still, we start with air, and at the beginning, we compress it. So, we have air inside the cylinder. At the beginning of a compression stroke, we compress it in one stroke. At the end of that compression process, we then have our heat input process. If this were a spark ignition engine, that is a gasoline engine, that is the Otto cycle, then we assume that the heat input is done at constant volume. On the other hand, if we have a diesel engine, the diesel cycle tells us that the heat input is done at constant pressure. So the processes are a little bit different, but the methodology that we use to analyze is very similar. And then we also would recognize that after the heat input process, then we would have an expansion process. We would call that the power stroke in a real engine. But that's where the high temperature, high pressure combustion gases, in our case air, is pushing the piston down and creating work. I should note that in a diesel engine modeled with the diesel cycle, work is done not only during the isentropic expansion after heat input, but work is also done during the heat input process, right? Constant pressure heat input occurs as the volume increases. So you have P delta V, in other words, work for that constant pressure process while heat transfer is taking place, in addition, again, to the work done during the isentropic expansion process. So that was the nature of our diesel and Otto cycles. Again, both were done using constant and variable specific heats, and hopefully I made it clear that variable specific heats is better, right? It's more accurate. I mean, it's still an air standard model, so you know, take ME412, or I guess it'll be ME4121 or 4120 once we start semesters next year. But nonetheless, that's internal combustion engines, and in that class you'll learn more about how one analyzes you know, real internal combustion engines. I teach that course, by the way. I always like to plug my courses, right? Nonetheless, so that's something to think about. But for now, air standard, variable specific heats is better, it's more accurate, and you know, you want to understand how to solve using both methods, but certainly variable is going to be emphasized. After that, the next gas power cycle we looked at was the Brayton cycle, right? And here we looked at modifications to the Brayton cycle compared to what you covered in ME301. In ME301, your first course in thermo, you just covered the, well, still an air standard cycle, but we just covered the simple Brayton cycle. We have flow through a compressor, right? Isentropic compression. Well, actually isentropic, but we did look at the non-ideal case too. But first we looked at the ideal case. We had isentropic compression, we had constant pressure heat input, we had isentropic expansion, we had constant pressure heat rejection or heat output. First we looked at that, assuming that the processes of compression and expansion, that is the work processes, were isentropic, right? Ideal, adiabatic, reversible, many names for the same thing. So that was the first thing we did, but then we also looked at the non-ideal case, right? We looked at isentropic efficiencies, both for the compressor and for the turbine, and we factored that into our cycle analysis. And then we added things to the cycle to make it more efficient. We're trying to minimize the compressor work, we're trying to maximize the turbine work, right? In other words, minimize the work input that we have to pay for, maximize the work output that we sell to our customers in many shapes and forms. So that's what we're trying to do here. And in order to do that, we modified the cycle a little bit. We looked at a regenerative cycle, regenerative Brayton cycle, where you take the exhaust from the turbine. Again, these are air standard cycles, so I use the word exhaust, but in our case it's just air. Nonetheless, the air coming out of the turbine goes into a heat exchanger called the regenerator. It exchanges heat with the air that has come out of the compressor, and that preheats the air then going into the combustion chamber, which requires therefore less heat input in the cycle and therefore improves the overall efficiency. We also looked at using multiple compressors in stages. And in this class, we only looked at the situation with one intercooler between two stages of compression, although in the real world, you could certainly have multiple stages of compression with multiple intercoolers to even further minimize the compressor work input. And then we also looked at something similar with regards to the turbines. We looked at multiple turbine stages with reheat in between. And again, in this class, we just looked at one reheater in between two turbines. But the reality is we could certainly have multiple turbine stages with multiple reheaters. And then after we did that, we looked at everything, right? The regenerative Brayton cycle with intercooling and multiple stage compression, and with reheat and multiple stage expansion, and for the non-ideal cycle, right? So you have to include isentropic efficiencies as well. So that was our Brayton cycle analysis. And then beyond that, we moved on to the Rankine cycle. The Rankine cycle is not an air standard cycle, right? The Rankine cycle is a steam cycle. In the Rankine cycle, we're taking heat, we're adding heat to water, that turns the water into steam. We run the steam through a turbine, and that produces work, and then we condense it back into liquid water, and we start all over again, right? We compress the water in a pump up to the high pressure of the boiler and add more heat in the boiler, and that's our Rankine cycle. Constant pressure heat input, constant pressure heat rejection, just like the Brayton cycle, except that in the Brayton cycle it's air standard, in the Rankine cycle it's a steam cycle, so certainly we have to use our steam cycle data, our water data, if you will, from tables A4 through A6 in our book. After looking at the ideal Rankine cycle, in other words, isentropic compression by the pump, isentropic expansion in the turbine, then we looked at the non-ideal case, using pump and turbine isentropic efficiencies. And then we made modifications to this system too, right? We looked at the situation where we have reheat with turbine stages producing work around that reheater, very much like we would have seen in the Brayton cycle. And then we also had a regenerative Rankine cycle, but the regenerative cycle was different than it was for the Brayton cycle, right? Here, our regenerative cycle will actually take some steam off of the turbine at some intermediate point. We call this extraction steam. So we extract steam from the turbine and we introduce it into a mixing chamber that we call an open feed water heater. Feed water coming out of our pump then mixes with the extraction steam, and that effectively preheats the feed water. Then we take that preheated feed water, we pump it up to the pressure of the boiler, and, well, the steam is created in the boiler and the cycle continues. But nonetheless, that was our Rankine cycle, right? Regenerative Rankine cycle with open feed water heater, with one open feed water heater. You could have multiple feed water heaters, but we're only going to look at one. We could have open as well as closed feed water heaters, but we only looked at the open feed water heater, so don't worry about the closed feed water heater. That's not something we covered. That's not something I'll test you on. But nonetheless, we looked at the complete cycle, right, that had reheat, that had open feed water heater, that had non-isentropic expansion and compression, and that was our Rankine cycle. Okay, so that was the next cycle we looked at. And then one more cycle, which is our refrigeration cycle. The only cycle we looked at in terms of analysis was the vapor compression refrigeration cycle. Here, we're going to take heat out of whatever we're trying to keep cold, let's say the food in our refrigerator, and that's our heat supply. It's a low temperature heat supply. We add heat to the refrigerant in the device we call the evaporator, and the refrigerant turns from a two-phase mixture into a saturated vapor. We compress that in a compressor. We can analyze the compressor either as isentropic, or eventually we analyze it as non-isentropic with compressor efficiency. But nonetheless, we compress it up to the high pressure of the system. At that high pressure, you have a very high temperature, so you can then transfer heat out of that high temperature refrigerant into the environment through the device we call the condenser. And in transferring heat out of the refrigerant, well, it condenses. I mean, we start with superheated vapor, we condense it into a saturated liquid, and then that saturated liquid is allowed to flow through a throttle back down to the inlet of the evaporator, and the cycle takes place again. We also looked at the absorption refrigeration cycle, but that's really quite complicated and well beyond this course. So besides just discussing it a little bit, there was certainly no analysis. So that was our final cycle, and that really took us to about the halfway point in the class. Then we looked at thermodynamic property relations. Here we were looking at the various equations which ultimately would be used to generate the thermodynamic property data that we have now come to know and love. We know that we need that property data for solving any problems. And having covered thermodynamic property relations, well, maybe we have a better understanding for where that data came from. Now, in this class, I certainly did not emphasize that. That's not something I choose to do, or really any of us choose to do here at Cal Poly. But nonetheless, we could at least see how it would be utilized. The data that I would typically give you wouldn't be experimental data, but it would actually just be the data right out of your property tables. You'd have a type of analysis that I might just call bounding analysis, where you'll look at your particular state point and kind of bound it with data above and below, side to side. And then using that bounding data, you could then determine things. You could validate one of the Maxwell relations. You can use, say, the Clapeyron equation to determine the enthalpy of vaporization, HFG. You could use these equations to find other things, gas constants, heat capacities, well, I should say specific heats, entropies, internal energies, enthalpies. I mean, we spent some time talking about that, but again, it wasn't the emphasis. Nonetheless, that was the next topic that we covered. Following that, we talked about mixtures of gases, ideal gas mixtures. With ideal gas mixtures, this is where we first learned about, well, really all sorts of things. We learned about the notation and the terminology associated with mixtures. We looked at Dalton's law and Amagat's law. We learned about partial pressures. We learned about mixture pressures and mixture volumes versus partial pressures and partial volumes. We looked at mole fractions and mass fractions. We learned how to calculate the gas constant for an ideal gas mixture, how to calculate the molar mass for an ideal gas mixture, how to use that data then. We could find specific heats for mixtures, et cetera, et cetera. But nonetheless, we at least learn how to use these various relationships for gas mixtures. And then ultimately I said that, we're still going to be solving first law problems. I mean, just because we're dealing with mixtures doesn't change the nature of the problem. So, I went through a couple problems anyway that just illustrates how we would solve the same kind of problems you've already seen, either closed or open system first law problems, but with a little twist, right? The little twist was that we have a mixture, so we have to calculate the mixture properties and use those mixture properties. And those would include properties for internal energy and enthalpy and entropy and specific heats and really whatever we want. Nonetheless, since we were dealing with gas mixtures, we were only dealing with ideal gas mixtures, and the relationships were relatively simple and straightforward. We didn't deal with real gases at all. Certainly there's sections in your textbook that deal with real gases. I did not assign those. I only assigned up to section 13.3 in your book. So make sure you don't cover material that, well, I should say, make sure you don't spend too much time studying material that you're not responsible for. After talking about gas mixture equations, then we talked about everybody's favorite ideal gas mixture, which is air-water vapor mixtures. It's all around us. We breathe it every day. We use it for various processes. With air-water vapor mixtures, first we looked at some terminology, some notation. We learned about things like specific humidity, also called absolute humidity, also called humidity ratio, omega, right? We looked at relative humidity. We talked about wet and dry bulb temperatures. We had various equations which we were able to then utilize to calculate some of these various parameters. We learned about how to calculate enthalpies. We realized that the enthalpy data in your water tables, A456, has a different reference point than your air data in table A17. So we can't use the data in table A17 and the data from A4, 5, and 6 in the same problem. They have a different reference state. So we basically chose the reference state for water, and then we can use our water tables for air. However, we have to use a calculation, an equation, in order to find the enthalpy of the air. But nonetheless, this is what we covered. And then finally, we looked at the psychrometric chart. We realized that we don't have to go through these many, sometimes tedious equations to find things like the absolute humidity or the relative humidity or whatever. We could use a psych chart. If we have two properties like the wet and dry bulb temperature, we can go onto our psych chart and we just read off all the rest of the data. We do remember, of course, that whether we use equations or whether we use a psych chart, all of our data for the mixture is per unit mass of air. Okay? Whether it's SI or British units, it doesn't matter. It's per unit mass of air. So I cautioned you many times to make sure you write down what your units are. Is it air? Is it water vapor? Is it mixture? So that'll just make it a little bit easier if you keep track just by putting subscripts in all your various terms. We also, at about the same time, talked about dew points and why dew points are important and how to calculate the dew point. I mean, we could calculate the dew point based on equations, but it's certainly a lot easier to use a psych chart. We just go to our point and we move horizontally until we hit the saturation line on the psych chart, and that temperature at that point is the dew point. It's no more complicated than that. But anyway, that was something that we then talked about. And once we had a good basis of understanding of air-water vapor mixtures, then we talked about air conditioning. Now, certainly you're all going to be able to take ME 418, or I guess it'll be 4180. It's an air conditioning class. You all have to take either a class in air conditioning or thermal systems, which is 427 or 4270 next year. But if you're interested in air conditioning, then take the 418 class as your thermal fluids requirement. But nonetheless, we covered air conditioning, all sorts of different processes. We looked at simple heating, we looked at simple cooling, we looked at dehumidification by cooling, we looked at simple heating plus humidification. We even talked about dehumidification by cooling plus reheat, where we would dehumidify by cooling, we get to the saturation line, we keep cooling, so water vapor condenses out of the air, and then we reheat because, often at the end of that process, the temperature is too low and the humidity is too high. So we looked at all these different types of processes. We also looked at the swamp cooler, evaporative cooling, if you will. And then the last process in air conditioning wasn't even an air conditioning process, right? It was the analysis of a wet cooling tower, which uses the same kind of information. We have water that's dripping down through the tower. We have air that's blowing up through the tower. They exchange heat, they exchange mass. In other words, water evaporates out of the dripping water stream and
turns into a vapor, and of course that creates a significant amount of cooling effect. It takes a lot of energy to evaporate water into the air, and that energy comes out of the water, so the water cools significantly in a wet cooling tower. So we analyze wet cooling towers, and then last but not least is chemical reactions and combustion. I summarized that at the beginning today, so I don't think there's any point in going through that again. So these were the topics we covered. By the way, I'm only going off the syllabus. I haven't done anything. It's not like I'm reading notes here so I make sure I remember what we've done. I mean, this is what we covered, so this is what we should know, and hopefully you'll know it as well as I do, at least by next Wednesday at 9:10 in the morning. At 11:10, you can forget it all. We've all been there and forgotten all sorts of things we shouldn't, but just make sure you do well and study hard before then. Anyway, are there any questions then based on any of this? Anything that I covered, did it bring up a question in anybody's mind? Any thoughts, issues, problems with problems? Questions on homework problems, questions with some of my example problems? Yeah.
So for the final, or for the last midterm, you had said that
Okay.
for property relations, we don't have to like bog down our equations.
Right, the same thing will apply here. In fact, let me just talk about the final since I'm not seeing any other questions about content. So first to answer your question, yeah, you're still allowed to use one 3x5-inch note card written on both sides. I will give you whatever thermodynamic property relations you need to solve a problem of that type. So don't clutter up your diagram, don't clutter up your 3x5 card. I mean, quite frankly, there are so many equations we covered in that section. You could fill up multiple 3x5 cards and you won't have room for anything else. So yeah, just make sure that you don't waste space on your card with thermodynamic property relations. It's not going to be necessary. I'll provide you with that equation. Anyway, as far as the test goes, there's not going to be any there's not going to be any general section. I mean, often on my final exams, I'll have maybe 10 or 20% just asking you about notation, terminology, just simple questions, just to make sure you can, let's say, show me you understand the language of thermodynamics. I'm not going to do anything like that. It's just going to be problem solving. So there will be a total of 6 questions on the final. Some of them are going to be short and will probably take 10 or 15 minutes, and others might take you 45 minutes to an hour. It really just depends. It could cover anything we've covered in the entire course. I would always emphasize material that you have not yet been tested on. So I'm pretty sure I mentioned already that you've not been tested for sure on anything dealing with air-water vapor mixtures, air conditioning, combustion. So you could pretty well bet there's going to be something dealing with that material on the final exam. But then that's just the emphasis. I could still test you on anything, even material that you've already seen problems on your first or your second midterm. So again, the emphasis on what you have not yet been tested on, but certainly everything will be covered. So you'll be able to use your note card. You'll have the thermodynamic property tables, the handout that I will give you. I'm also going to pass out a psych chart to every one of you in the appropriate units. So you're not going to have to worry about, maybe you have your own property tables. And I mean, I remember my psych chart. I was always too lazy to get a copy of it, so it was so hard to read. There were dots and lines all over the thing. You don't have to bring in your own fresh copy of a psych chart. That will be part of what I'll give you. Now, certainly if you have your own property table handout, you can bring that instead of the one that I give you, but it's entirely up to you. But you'll definitely be able to use the psych chart. You'll be able to use table A17, your air tables, and of course all the other tables that are in the handout. I would also just remind you that sometimes my tests are too long. Now, I've had students finishing every one of my tests early, but most students don't. So if the test is too long, if you don't feel you'll have enough time to complete it, then at least set up the problems, make it real clear where your data comes from, how you would solve the equations you put down on your page, what order, how the results from one problem might be used for another problem, or I should say might be used for a future portion of the same problem. You can use numbered or lettered equations. You can use arrows that point all over the page. I mean, I've seen it all over the years. You could certainly do whatever you need to, but again, if you don't feel you'll have enough time, set up all the problems first and then just go in later and plug in all the numbers. If it's clear that you understand how to solve the problem and all you don't have is time to finish it, certainly you'll get at least passing credit on that particular problem. So again, you're all certainly welcome to do that if you want to. So I think that's pretty much what I wanted to mention regarding the final. Any other questions on the final exam? Format, content? We know it's going to be in this classroom. Okay. So then, are there any questions? Again, just in general, homework problems, example problems. You guys all want to get out early, I bet. Some of you probably have friends who are giving presentations in the projects. Project symposium is today. The ME students' presentations are like next door and then a couple doors down. And there's one that should be going on now. Another one starts at 11:20. There's one at 11:40 if anybody's interested. But anyway, was there a question I thought I had? Yes?
So we're allowed one card front and back?
Yes. By the way, even one card is not a whole lot of space, right? So once again, use your space wisely. If it's material that you know, then don't bother to put it on your card and waste space. I can't imagine anybody doesn't know how to calculate an isentropic efficiency, right? Actual over ideal work for a turbine, ideal over actual work for a pump or compressor, and of course, work is just the enthalpy change. So do you really need to put that on your card? Some of you, but hopefully not. Nonetheless, so think about it. Don't just fill up your card and then not be able to understand what you've written because everything's so tiny. I've had students that just do everything, make a big 8.5 by 11 sheet, and then take it to a copy machine and just keep shrinking it down until it's 3 by 5. You're welcome to do that too. Yes?
So are you going to give us the TS diagrams that relate to this cycle?
No.
Midterm could have one.
There are times when I might do that. Sometimes, honestly, it's easier for me to grade a problem if I either give you a schematic or a TS diagram or a PV diagram and give you the state points, because then I know that every student's going to use the same state points when they submit their work. If I don't do it that way, then everybody's state points are different and it makes it really, really hard to grade. So there are times when I might give you a TS diagram, I may give you a schematic diagram, but I also may not. There's times when I'll ask you to draw a diagram. I'll certainly ask you to solve problems, but I may also say, show me on a TS diagram, the Brayton or Rankine cycle, show me on a PV diagram, the Otto or diesel cycle. Those are pretty common things I could ask you to do too. Yeah. Yes?
So on the second midterm, you gave us for some problems you gave us these at certain points. So
Yes.
This time are you going to do that as well?
That's very possible, yeah. Some of these problems, are just so lengthy that, it could take you just 20 or 30 minutes doing nothing more than pulling numbers out. So yes, it is very possible I could give you certain numbers, but I don't have to. It depends on the problem. So, yeah. But yeah, sometimes.